Hello. Today, we're going to talk about dimension reduction. This will be the first unsupervised learning task that we'll discuss. Dimension reduction is unsupervised learning, so the output is unknown. Also, the output is continuous. Today, we'll cover what is dimension reduction, how we might use it. We'll focus mostly on one technique called principal component analysis, but we'll also have a quick review of two other techniques. So what is dimension reduction and why might we use it? So let's recall how we are imagining that the data is structured. We're imagining that each row is an observation and each column is an input variable. We can visualize every pair of variables in the scatter plot. So for example, we could plot each of the observations as dots and compare their values of variable 1 versus variable 2. We can then compare variable 1 versus variable 3, and so on. Each variable we can call a different dimension. And so, for example, in this table, this would be 5-dimensional data. However, it is very hard to visualize high-dimensional data. So, in dimension reduction, we try to describe the high-dimensional data in a low-dimensional space while maintaining as many properties as possible of the original data. For instance, if the original table has 50 columns, then if we were to draw a lot of pairwise scatter plots, we need to do 1,200 pairwise comparisons. However, with dimension reduction, maybe we'll be able to come up with a new table that just has 3 columns, and then we'd only need to do 3 pairwise comparisons. All we'd have to do is compare variable 1 to variable 2, variable 1 to variable 3, and variable 2 to variable 3. So why is this machine learning? Well, what we want to do is to predict a continuous variable or variables from input data, and we want to train a model that does this using a training data set. However, we don't know what the meaning is of this continuous variable. So instead, we try to come up with a continuous variable that somehow describes the data well. Let's make this more concrete by looking at a specific technique, principal component analysis. First, I'll describe principal component analysis in the following scenario. Let's say that our original data has 2 variables, and we want to condense the table so that way there's only 1 column. We could draw the original data as a 2D scatter plot, where each dot is an observation, and this is variable 1 and this is variable 2. First, what we can do is we can draw a line of best fit. In this case, it's different from the line of best fit that we learned about in the previous section, because in this case, we want to minimize the square distance between these points and the line. So as you recall, in normal linear regression, we consider the residual, which is a vertical line. But here we have a line that's just orthogonal to the line of best fit. Once we have a line of best fit to the data, we can squish the points onto that line of best fit. Then we can take that line and rotate it. The distance that these points are along this line is their value in terms of the first principal component. Let's extend this to 3D. So now let's imagine that we have 3 columns and we want to describe it in terms of 2 principal components. So the first principal component will be the line of best fit. So then the second principal component will be the second best line of best fit that is at a 90-degree angle to the first line of best fit. And remember that the best fitting line is defined as the one that minimizes the average squared distance from the points to the line, which is a slightly different definition as the one we used in the previous section. And also remember that all of the principal components are at right angles to each other. This is called being orthogonal. When you do PCA, it's extremely important to scale your data. For example, here you can see that this would probably be the line of best fit. However, if the data wasn't scaled and variable 2 had a much wider range than variable 1, then by the definition of the line of best fit, this would be the line of best fit. This is because a small change in variable 1 won't make much of a difference in terms of the distance to the line. However, a small vertical change would make a huge difference. You can visualize it this way, where if you were to draw this to scale, then the x-axis would be very narrow and the y-axis would be very wide. And so you would think in this case that the line of best fit would be a vertical line. Therefore, the data should always be scaled before you do a principal component analysis. So how do you visualize the results of a principal component analysis? Well, we can start off by drawing the data points in terms of the principal components. So here, the x-axis is principal component 1, and the y-axis is principal component 2, and each x represents an observation. We can also look at how much of the variability each of the axes explains. So in this case, the first principal component explains 40% of the variation in the data. The higher this number, the more this principal component explains the variation in the data, and so the more information about the structure of the data is captured by the image. You can also color code the points based on specific characteristics of interest. You can also look more carefully at the equations for each principal component. Each principal component can be described as a linear equation including all of the input variables. So, for example, a large coefficient in front of one of the variables would indicate that this variable is more important for this principal component. Let's look at a few examples in the literature in which people used principal component analysis. For example, this recent paper looked at metabolomics of individuals with different kinds of urethral birth defects. They plotted every individual as a point based on their principal component 1 and principal component 2. Next, they color-coded the points based on the type of birth defect. Next, you can look at the variation that each principal component explains. The first principal component explains over 50% of the variation in metabolomics between individuals. Next, they color-coded the individual points based on a type of urethral birth defect. And you can see that in general, the type 1 birth defect has higher values in principal component 1 than type 3. This means that there might be some metabolomic differences between the different types of birth defects. Here's another example from the literature. In this case, they looked at genotypes of different individuals from South and Central American countries. And they graphed it across 3 different principal components. As you can see, there's some separation based on the country of origin of the individual. For example, individuals from Cuba and the Dominican Republic tend to be up here. Let's quickly review 2 other ways of doing dimension reduction. One is an autoencoder. An autoencoder is a little bit like compression. So in compression, you can imagine taking an original image, and then if you want to transfer it, like an email or something, often you'll compress the image into a compressed format. This is like the dimension reduction step. Then the person who receives the email can then transform the data from the compressed format to a large image, just like the original. If the compression scheme is lossy, then the image might not be as sharp as the original because you would have lost information. Not all compression schemes are lossy. In an autoencoder, it's kind of like the same thing. You input a row of variables, and it comes up with a small number of continuous variables, which is like a compressed version of the original data. Then you should be able to use this smaller number of continuous variables to reconstruct the original data. So in essence, the machine learning question is, how do you calculate a small number of continuous variables so that the reconstructed row would be as similar to the original row as possible? T-SNE is a technique that has recently gained a lot of popularity, specifically in the community of people who look at single-cell resolution RNA-seq data. T-SNE is a way of exaggerating any clustering behavior that's in your data. For example, data points that are close together in higher dimensions look even closer together in the 2D space. Data points that are far apart in high dimensions look even further apart in 2D space. So this exaggerates cluster shapes. Then you can use clustering algorithms that we'll talk about in the next section to identify which points belong to which cluster. However, there's lots of warnings associated with T-SNE. First of all, it will probably show clusters even if there are none in the original data because it accentuates any clustering effects. In addition, T-SNE produces a random figure every single time you run it, which means that you want to be able to run the T-SNE algorithm multiple times in your data and make sure that the results are consistent. Also, there are some free parameters, and you should run T-SNE with different sets of parameters because the results might vary, and you want to see if the results are robust. In summary, dimension reduction techniques can help with data visualization. Principal components analysis is one specific technique for mapping data into lower dimensional space that captures as much of the variation in the points as possible with linear transformations. Autoencoders are ways of compressing data into lower dimensional space in such a way that you can predict what the original data was as well as possible. In T-SNE, you visualize data in a way that accentuates any clustering that might be present in the data. This is a good segue because next week we'll cover clustering.